All right, so here I'm going to talk about Newton's law of gravitation, and then I'm going to talk about Coulomb's law. Um, Here in the top right corner, you can see that I have this little formula. F is the force, force of attraction. So gravity is an attractive force. I'll just write that here. It's an attractive force. What does that mean? It means that the force wants to pull the two masses in this formula, mass one and mass two. It wants to pull them together. And so the way that this formula works is that I have a mass one, and I have mass two. Oops, have my mass two, and the force of attraction between them, F, which I see here, is governed by this equation. It states that the force is equal to the G is called the gravitational constant. That's literally just a scalar constant, constant of proportionality. It's a fixed value, a constant value for gravity, and the formula is that force is equal to gravity, the gravitational constant, multiplied by the first mass times the second mass, and then that whole thing divided by the distance between the two. So the distance I have down here, the distance between the two masses squared. And again, this is an attractive force. What this formula basically tells us is it tells us the force that one mass exerts on the other mass. And interestingly enough, each mass exerts that same force on the other mass. So down here, I have F m1 m2. That is the force. Let me write this out. Force exerted on mass 1 by mass 2. And so then the other force is the opposite. It would be the force exerted on mass 2 by mass 1. And you can see just with the bottom one here, let me go back to this guy. That is the force. It's pulling mass 1 towards mass 2. That's the force exerted on mass 1 by mass 2. And then here, this is the force that's pulling mass 2 towards mass 1. And so now I want to move on to the next slide, which is Coulomb's law. And it looks strikingly similar, and it is strikingly similar. This equation up here, again, this is called Coulomb's law. And it is the force of, well, in this case, it's a force of attraction because it's a positive and a negative charge. I'm going to write here that this is attractive because it's a plus and a minus. If the two charges were the same, say this was a minus and this was a minus, then I would have not an attractive force. I would have a repelling force. Oh, they would for some reason I can't think of the word for it right now, but they would not be attracting each other. They would actually be repelling one another. Maybe it would be just called a repellent force. And so, but in this case, just to recap, let me go ahead and write the previous equation here. This was G times m1 times m2 divided by the distance squared. Distance squared. That was the equation from the previous slide. And now we can see that, again, we have a constant that's called Coulomb's constant. But instead of scaling this constant by the mass 1 times mass 2, we're scaling it by charge 1 times charge 2. So in this case, I can say that my positive charge over here, my positively charged object has a charge Q1, and my negatively charged object has a charge Q2. Some quantity of the magnitude of the charge for that particular object or particle, whatever it may be. And it just, to me, is so shocking that the two equations are so similar. Again, it's the force multiplied. Force is equal to the constant multiplied by charge 1 times charge 2 divided by the distance squared. So strikingly similar to the gravitational law, Newton's gravitational law. And again, I have my first force down here, which is the force exerted on Q1 by Q2, and that's pulling Q1 towards Q2. And then in the top, I have the force exerted on Q2 by Q1, and that is pulling Q2 towards Q1. And so what's really interesting to me is just how similar these two laws are. And, let's go back to this slide for just a second. You could imagine if you have the Earth, let's just say that this, again, is the Earth, and you have this is some huge mass, the mass of the Earth. And then this is some little ball out in space, maybe some distance from the Earth. If you were to just release that ball into the Earth's gravitational field, it would exert a force, Fm1m2, on the Earth that would pull the Earth. But that force is so negligible compared to the mass of the Earth that the Earth is not going to move. But rather, the same force is exerted on the ball towards the Earth, and that the Earth will then pull the ball towards the Earth and into the atmosphere, and it would burn up, no doubt. Something similar happens in terms of charge, and in the next, obviously not the burning up part, but in the next slide or the next video, I'm going to talk about that a little bit further. I just really wanted to give an idea of the similarity between these two laws, because I think it gives a good picture of how charges move around and why they move the way that they do.